Alright, welcome to lesson 9.05. Here we're going to start calculating the volume of solids that are formed by revolving a region around the x or y axis, sometimes called solids of revolution. And we're going to use definite integrals to do this. Let's get started. Alright, before we get started with the discovery problem, I want you to go back to our definition for the volume of the solid that we looked at in 9.03. And remind yourself of the components that we need in order to calculate the volume of a solid, namely the cross-section and the area of that cross-section. Alright, once you've done that, let's take a look at this problem. The region R is bounded by the curve f of x and the x-axis on the interval from -2 to 2. You can see that region there. This region is revolved around the x-axis to create a vase-shaped solid. Find the volume of the solid. Okay, so let's imagine what happens. This region here is going to be revolved around the x-axis. So you're going to hold the x-axis constant and you're going to revolve this area around it 360 degrees. Okay? What I'm going to do is I'm going to draw what this will look like, and hopefully that envisioning of the finished solid will give you some intuition as to how you might calculate the volume of this solid. So let's take a look at that. Alright, so I've redrawn my curve here, and what I want to envision is this region being swept around the x-axis to create a solid. So to help us understand what that's going to look like, imagine you took one tiny little strip of this region. Imagine this strip here, and you revolved it 360 degrees around the x-axis. What would you end up with? You'd end up with a little cylinder, right, that has a radius of exactly this distance here, goes all the way around the x-axis. And that's going to be true for every tiny strip of area in this region. When I revolve it around, it's going to create a little cylinder of its own. And the radius of that particular little piece of cylinder is just going to be the height of this curve. So that should give you some intuition about what those cross sections are going to look like. Now to draw this, notice that this piece here is going to create a little cylinder with this radius. This piece here is going to create another little cylinder with this radius. So it's going to come down here, and what you'll see is I really just have a reflection of this curve over here with these little cylindrical pieces going through. So now I've drawn my reflection of my function, and what I want to envision are these thin little cylindrical cross sections all the way through to give it this three-dimensional shape. Just like that. So hopefully here you can see these little cross sections all the way through. And now with these cross sections in mind, you can use our definition for finding the volume of a solid to find the volume of this solid using the definite integral. Go ahead and take a couple of minutes to try that now, and then press play and we'll take a look at how we might do this step by step. Alright, hopefully that went well. Let's go ahead and take a look at this step by step. So what I want you to do is complete each step on your own, and then go ahead and press play and we'll take a look at it and move on to the next step. So first, draw a single cross section for the solid, and I want you to draw this one on the original region that we had sketched here. Alright, so here is my cross section. Notice it's very similar, obviously, to the cross sections that we drew when we drew the solid out. Alright, now our goal is to label the radius here with an expression in terms of f. So we want to determine what the radius of our cross section is. Alright, this should be pretty easy. It's very clear that no matter where my cross section is, the radius will be determined by the y coordinate of my curve. In other words, simply by the value of f of x. Alright, now what you want to do is write a function, a of x, for the area of this cross section. Alright, so since we're dealing with a cross-section that is a circle, the area of a circle is pi r squared, and so we have pi. In this case, our radius is simply the value of f of x, so it will be pi times f of x squared. Alright, next question. What is the width of each of these cross sections? Well, obviously this depends on the number of cross sections, but if I want infinitely many, we know that those widths are going to get infinitesimally small. In other words, they will become dx. So the widths are dx, and the area is pi f of x squared. So when I multiply the area by dx, I will have the volume of a cross section, and this should lead pretty simply to the final step. Write and evaluate a definite integral for the volume of the solid. Alright, so if you needed a little bit of a hint, remember that the volume we can determine by taking the area of a cross section, multiplying by the thickness of a cross section, and simply summing up those cross section volumes from A to B. So remember, we're thinking of the volume of a cross section, and we're simply adding these all up, or taking the definite integral from A to B. So in this situation, this is what we'll have. The integral from -2 to 2, our limits of integration, of pi times the radius, which is f of x, 2 plus x cosine of x squared dx. And this, of course, is going to give me the volume, the infinitesimally small volume of my cross section, and I'm adding those up from -2 to 2. Of course, I can make this a little easier, and I can factor out the pi, and write it like that. And we can go ahead and evaluate using our calculator. To get a volume of 52.43 units cubed. And before we add into our notes, I want to take a look at this and see if we can draw any generalizations. Any time that we revolve something around an axis, what type of cross sections are we going to create? Well, it doesn't matter what our curve looks like. Any individual point that we pick when we revolve it around something is going to form a circular cross section. So the great thing about solids of revolution is that the area of our cross sections are going to be related intimately to the area of a circle. Let's go ahead and record a few of these key points now. Okay, so this is the definition for calculating volume that we've already discussed, and we've already talked about one way that we can build a solid given a region for the base, the type of cross section, and the orientation of the cross sections, of course using this definition. And now we have another situation where we can be given a defined region and an axis of revolution. In the situation we just saw, that was the x-axis. And what you want to notice is how the process is really exactly the same. Because I'm using the same definition, what I am trying to find is the area of my cross section, so that I can then take the area, multiply it by the thickness to find the volume, and add those up over my interval. What I want you to do right now is go ahead and make sure you get these steps down, and then I want to talk about them briefly. Alright, so notice that the process is really exactly the same. We're going to sketch the region if it hasn't already been done for us. You may, this is optional here, sketch the solid itself, and how we do this, as I did previously, is reflect the curve, and we'll see with multiple curves in a bit. Reflect the curve over the axis that you're revolving, and draw circular cross sections to connect them. And then you want to sketch a cross section and identify the dimensions. So given your region, sketch a cross section and identify the dimensions. Remember, these cross sections are going to be circular because we're revolving 360 degrees around an axis. That means our cross sections should always be circular. Okay? And that means that the dimension we're looking for is the radius. Then of course we're going to construct a function for the area of any cross section. Guess what? If they're circular, we already know that function. We just need to apply the proper radius. Identify the limits of integration, and then write and evaluate our definite integral to find the volume in units cubed. Alright, so I want you to go ahead and leave little space underneath here, because with solids for revolution there's a good bit of flexibility with respect to all the different characteristics that our revolution can take, and so there will be a sort of a couple of different things you'll want to add here just to make sure that you're solid when you go back to look at your notes. Alright, let's go ahead and get started. Let's try this one here. Let R be the region enclosed in the first quadrant by the graph y equals 4.5 minus x squared over 2. We want to go ahead and find the volume of the solid generated when R is revolved about the line y equals 0, the x-axis, and also find the volume of the solid generated when R is revolved about the y-axis, or the line x equals 0. So make sure you follow your protocol here. First things first, go ahead and sketch this region R here, and then work through part A on your own first. Follow those steps. Trust yourself. If you think you get stuck, reason it out on your own, and then we'll take a look at it together. Alright, once I've sketched the region here, I have an option. I can go ahead and sketch what the whole solid will look like quickly, or I can just envision it and then take a look at one cross section. For the time being, as we're getting started, I think it's helpful to go ahead and sketch the whole solid. So I'm going to do that quickly, and the way I'm going to do that is simply, I notice that I'm reflecting over the line y equals 0, the x-axis, so I'm simply going to reflect my curve over the x-axis and draw those circular cross sections. So now that I have a pretty clear idea of what my solid is going to look like, I can go ahead and sketch a singular cross section here and follow through with my game plan. So go ahead and do that now, and we'll take a look. Alright, so having drawn my solid, it's very easy to draw a cross section. Of course, it is circular here since we're revolving around an axis, and therefore my dimension is going to be a radius, which is the y-coordinate of my curve. And so therefore the radius is going to be 4.5 minus x squared over 2. And since I'm dealing with a circular cross section, I know the area is going to be that radius squared times pi, as we can see right here. So since this gives us the area of a cross section, and we know that the thickness of each cross section is simply dx, we now know that we can find the volume of each cross section by multiplying the area by dx. And then when we sum over the interval from 0 to 3, we will end up accumulating the entire volume of the solid. So we represent our infinite sum using a definite integral from 0 to 3 of the product a of x times dx, inputting my function for a of x here, and then evaluating, I get 101.788 units cubed. Alright, let's take a look at part B now. Go ahead and try part B again on your own if you haven't already, and then we'll take a look at it together. Okay, so the only difference here is that I'm revolving my region R around the y-axis, the line x equals 0. So I can imagine each thin strip of my region R being rotated 360 degrees around the y-axis, forming these very thin cylinders. And each of these cylinders stacked on top of one another is going to give us this solid. Okay? So I'm going to go ahead and draw what that will look like. Remember, all I have to do is reflect my curve that gives me my region around or about that axis that I'm revolving. And then I can just draw these cylindrical cross sections going through, which will allow me to visualize my solid, just as I've done here. And of course we could fill this in a little bit to really represent that we have a solid three-dimensional figure. So once we have a good visualization, now we can go about actually drawing one singular cross section in our original graph. We can label the dimensions accordingly with respect to the curve that we have. That will allow us to write a function for the area of each cross section and thereby compute the volume of our solid here. So let's go ahead and do that. So here is my cross section. Of course it is circular, and so the dimension I need is the radius. Looking here at the radius, I can see pretty clearly that the radius is going to be the x-coordinate of my curve, right? The distance between the y-axis and the x-coordinate of the green curve. So I need to solve my function here for x so that I have an expression that gives me the x-coordinate. So I'll go ahead and do that. That will be my radius, and that will allow me to write my area function. Alright, so solving my equation here for x, gives me that the x-coordinate of my curve will be the square root of 9 minus 2 times y. And this is, of course, the value of the radius at any y-coordinate along my interval from 0 to 4.5. And that means that the area of each cross-section will be in terms of y. I can see this again because I noticed that the thickness is dy. Is going to be pi r squared, or by simplifying, it'll be pi times 9 minus 2y. And now, of course, noting, as I just mentioned, that the thickness of our cross-sections will be dy, we can use the definite integral to compute this volume. As I've shown that here, I'm simply applying my definition, and then I'm going to input my function for the area here, factored out of pi. I can find the antiderivative of this pretty easily and evaluate at 4.5 and at 0 and subtract, and then multiply by pi. So it'll be 20.25 pi units cubed. If you were to approximate that, it's probably somewhere around 63 units cubed. All right, at this point, go to the homework on Math Excel 9.05 and go through the first 3 questions, answer those in your notebook, and then go ahead and come back to the video and we'll tackle another type of revolution problem. All right, welcome back. We're going to take a look at another problem that is going to deal with something called washer-shaped cross-sections, very similar to what we've been dealing with already. If any of you ever put together a piece of furniture, when you're screwing in a bolt, you are going to put a washer in between the screw and the material that you're screwing it into to protect that material. And so hopefully you have an idea of what that looks like. Go ahead and copy down the question and the graph, and then press play and we'll take a look at what we can do together. Alright, so here we go. We know we're revolving this region S around the x-axis, the line y equals 0. We know that the two functions intersect at pi over 4, the green function is cosine, and the red function is sine. Now, before we get started finding the volume, we need to visualize what this solid is going to look like. So as we've done in the past, imagine that each strip of region is revolved around the x-axis so that it's forming sort of this cylindrical shape. But notice that there's going to be a little piece as we move farther and farther towards pi over 4, there are going to be these little pieces that are left out. And so if you were to revolve this region, you're going to get a sort of hollow cone shape in the center. So let's try and visualize that even better by actually drawing what this solid will look like, the same way we have previously, by reflecting both curves and then drawing some circular cross sections to connect those. So let's take a look at that. Okay, so here are the two curves, and here are the reflections of the two curves. And I'm going to go ahead and just shade in the actual area of the region. Now, I can pretty clearly see the pieces that are going to be left out. In other words, this cone-shaped hollow area. So to make that more clear, I'm going to connect the red curves with the circular cross-sections, as I have done here, and I can pretty clearly see that inside here is going to be hollow. In other words, it's not going to be included in my volume. The part that is going to be included in my volume is the part that's solid, and that's going to be the piece of my solid which is formed by the actual rotation of this area. Okay? So to make that very clear, I'm going to connect the green curves with circular cross-sections, as I've done here. And what you can see is that, okay, this is sort of the bottom of the figure. That's where the tip of the hollow cone meets sort of this back end of my rotation. And at any slice that I cut out, so if you take this, sort of green slice here, there's a little hollow in the center of it, which of course is another circular cross-section. So what I want you to do right now is go ahead and draw a cross-section of my shape. And I want you to note the pieces that actually contain volume and the parts that are going to be hollow. All right, so here's the cross-section that I've drawn. And notice, because I'm picking this point here, at every point around my cross-section, there's going to be a band of area that is this exact width. And so I can sort of shade that in as I go around my cross-section. I'm always going to have this band that contains actual volume in my solid. And of course there is going to be a center that is hollow. Now, to really get a grasp of how I'm going to compute the area of this cross-section, I'm actually going to pull it out and lay it flat so that we can analyze the components. All right, so here's the first component. That's going to be the outermost part of the shell, which is taken from revolving this point here around the x-axis, and that's going to give me, obviously, a circle. Now I'm also going to be revolving this much of the area, and so that's going to give me sort of this band of actual volume, and then in the middle there's going to be this revolution of this point around the red curve around the x-axis, which is going to give me another circle, and within that circle there is no area, there's hollow. So I'll draw that here, as I've done here, and now I want to denote the actual part of my cross-section whose area is going to matter. In other words, the part of my cross-section which is creating the solid component of my solid, as I've done right here. Now, notice, I need the area of this cross-section. I know that the thickness of this cross-section is going to be dx, and so if I can find the area of this cross-section that's creating the volume, then I can combine the two components to find the area of each cross-section and use the definite integral to sum those all up. So what dimensions do I need to know to compute the area of this cross-section? Well, I need the area of the green circle, I need the area of the red circle, therefore I need the radius of the green circle and the radius of the red circle. Right, so I've annotated those here. Notice that I'm using a capital R for the radius of my larger circle and a lowercase r for the radius of my smaller circle. This is a common mathematical practice, so you'll want to take note of that. Now, how can I find the radius of the green circle? Well, notice that that green circle was created by revolving this point on my green curve around the x-axis, and therefore the radius of this green circle is going to be the y-coordinate of the green curve, in other words, cosine x. And similarly, lowercase r, or the radius of the red circle, is sine of x, because this red circle was generated by rotating this point on my red curve around the x-axis. So now I have the radius for each of my circles, and now I can compute the area for the green circle and the area for the red circle and subtract the two. This will give me the area for my cross-section, which I've represented here visually and will allow us to more clearly understand why our area function for our cross-section looks the way it does. So let's just write that out. So starting with the area of the green circle, that's going to be pi capital R squared, which is pi cosine squared x. And similarly, the area of the red circle is going to be pi lowercase r squared, and so that's going to be pi sine squared x. And there I have the area of a cross-section. I can simplify this a little bit by factoring out a pi, and that's actually going to be helpful. It'll just make writing my integral a little easier, so I'll go ahead and do that. Alright, at this point I want to take a quick step back and notice that these are washer-shaped cross-sections, and this is exactly what a washer looks like. If you Google washer, you'll see these thin little pieces of metal that have a hole in the center where you can put a screw or a bolt and then screw it into the material, and this little thin piece of metal protects the material that you're screwing things into from the head of the screw. Alright, now taking note of the fact that these cross-sections have a thickness of dx, we can use the definite integral to compute the volume of our solid with the hollow center. It will look exactly like this. And we'll end up computing to 1.750 units cubed. This is actually pi over 2 units cubed. So really quickly, before we write down a couple of notes, we want to take note of what exactly will create washer-shaped cross-sections. Notice that this occurred because there was some blank space not in my region between my region that I was revolving and the axis that I was revolving around. So anytime we notice that there is some of that blank space between my region and the axis of rotation, we're going to end up with washer-shaped cross-sections, which are pretty easy to handle because once again we're just dealing with the area of circles. We just have to make sure that we subtract the area of the bigger circle and the area of the smaller circle to find the area in between. All right, let's quickly add some notes and then we'll get on to the rest of the homework. So adding this quickly to our notes about solids of revolution, we see that we can have circular cross sections, but also when there is a little gap between our region and our axis of revolution, we'll have washer-shaped cross sections, in which case the dimensions we need are the radius of the outer circular cross section and the area of the inner circular cross section. I've drawn that little diagram here. And so the washer-shaped cross section has an area given by the area of the outer circle minus the area of the inner circle. And here I've written that out. Notice, of course, that capital R and lowercase r, as they did in our example, are going to depend on the functions that define our region. And so, in practice, you'll actually be inputting, an expression that gives those particular radii. Also notice that we can factor out a pi here, so we can rewrite this expression as pi times capital R squared minus lowercase r squared. But this is as far as I can simplify. I cannot pull out this squared, and I'll let you think about why that's the case. So with this particular area function for my washer-shaped cross sections, I could now go and apply my definition by combining my area with the thickness and a definite integral to compute the volume. So let me just show you what that would look like if I applied it. There it is, and notice that I am simply applying my definition here. All right, go ahead and move on now to the second part of the homework. Be sure to email me or stop by if you have any questions.